Let's now start practicing using Kirchhoff rules and understand more about them. The loop rule can be used as often as the resulting equation is independent of the equation from the other loop equations. Equation will be independent as long as it contains at least one circuit element that is not involved in other loops. It will be obvious when we start doing it. So, another important part here is that when using the loop rule, pay close attention to the sign of the voltage drop across the current element. We're going to talk about it as well. And remember that you can go around the loop in any direction as soon as you are consistent. You're going to do fine. Directions in Kirchhoff's rule. The sign of the potential in Kirchhoff loop rule will depend on assumed current direction. Okay. Assumed current direction. What does it mean? We assume that the current will go a certain way, and that will define our signs. We may be wrong in our assumption. This way, when we'll solve the circuit, we're going to get negative sign, but it doesn't matter. It just means our assumption was wrong, but everything is correct. And our current will go into opposite direction than assumption was. Okay, let's keep going. Moving a parallel to the current, produces a potential drop across a resistor. What does it mean? Negative IR. So we have to take a negative sign, multiply current by this resistance, and that goes in the Kirchhoff loop rule. So if we're moving parallel to the current, moving the same direction as the current. If we're moving anti-parallel to the current, we'll have to add. So if it's against current plus IR. Okay. Hopefully when we'll try to solve a couple of problems, it'll be more clear. Let's go to the next slide. Kirchhoff rules number of equations. In general, if a circuit has n junctions, the junction rule can be used n minus 1 times. Okay? And then we're going to need a loop equation. In general, a loop equation will be independent of other loop equation if it contains at least one circuit element that is not involved in other loops. Let's look at this picture. We have a simple circuit with two resistors in parallel, R1 and R2. We assume that the current that goes through resistor 1 is current I1 and current goes down through resistor 2 is I2. We also assume that the current over here is I3 and it goes back over here, becomes current I3. Okay. We can have here three different paths. Path number 1 in the picture A goes through resistance 1. Path number 2 goes through resistor 2. And path number 3 goes in this little loop. So we have three equations. And how do we construct those equations? Let's start from this point in our pass through around the loop. I'm going around the loop. I see the battery connected minus to plus. This means we have to add voltage of the battery EMF. Then we go over here. We see current goes down and we go in a direction parallel with the current down. So we have to subtract I1 minus R1 and it's equals 0 because we coming back and we don't mean anything on our path. Similar way we're going around path 2, so it becomes EMF minus I2 R2 is equal 0. And when we go around this circuit, path 3, it's a little bit more interesting as far as I'm concerned. So let's look over here. We start over here and this is our path around the loop this way. However, we assume the current one goes this way. And now we're going anti-parallel to the current. We loop, our path across the loop is up in this point, but current down, so we need to add. So we're adding positive I1 plus R1, and then we go this way, there's nothing happening. Then we see resistor 2 we need to subtract now I2 minus R2. Why minus? Because direction is the same as the assumed current direction, and it is equal 0. It's not written on the slide, but I'm going to mention we can also have junction equations here, and it's going to be, we can have we have two junctions, so we can have one junction rule, and it says as I3 is equal I1 plus I2. If we look at this junction, it's pretty much the same. I2 plus I2 plus I1 is going to give us I3. So it's identical equation. So let's just look again. We have 1, 2, 3 unknowns for the current. We don't know current, and we're solving for current. And we have 4 equations. So we have a little bit too many equations. But why it is so? Because these 3 equations, they are not independent of each other. For example, what will happen if we add this equation and this equation? If we add those equations, EMF minus I1 R1 is equal 0. EMF minus I2 R2 is equal 0. Now let's do, we have to subtract. So we multiply this one by -1, that's what we'll get, and then we'll add them. We would have EMF minus I1 R1 plus I2 R2 is equal 0. So this cancels out. We have I1 R1 minus plus I2 R2 0. So over here in the bottom, our last equations was actually identical. It was I1 R1 negative I2 R2. So it's the same if we multiply it by negative sign, we get an identical equation. That means the third equation kind of hidden in equation 1 and 2, and that's why it's useless. It doesn't have any new information. So we're only using equation 1, 2, and the junction rule. So when we say that in general a loop equation will be independent of other loop equations if it contains at least one circuit element that does not involve another loop, that's what it means. That if we do any manipulation with first equation and second equation, there is no way we can get a third equation. So this way it's useful for us, otherwise it's not. Already said that before. This slide goes again about equivalent resistance, what's happened when resistors are in parallel. There is a formula. Equivalent resistance is equal sum of reverse, and you have to do inverse again. So this was opposite for conductors. For conductors, we had 1 over C equivalent is equal 1 over C1 plus 1 over C2, so on, when they were connected in series. Okay, so you have to be careful. Don't confuse which rule you use where. Some summary about circuit analysis. Some complex circuits can be solved by combinations of series and parallel rules. Okay, so you kind of have to simplify rule. Just look at one part and another part. This one parallel, this one series. You simplify it and you're solving it. Other circuits must be analyzed directly by Kirchhoff rules. You can say right away, any circuit can be solved by Kirchhoff rules. It will work anytime, every time. But by combination of series parallel rules, sometimes will not work. But this one always works. So if you know how to do this one, just keep doing it. You'll be fine. Connecting resistors in series always give a total resistance larger than resistance of any of the component resistors. Why? You have R1 plus R2 plus R3 plus so on. Resistance is always positive, so equivalent resistance is always going to be larger than any of those. However, connecting resistors in parallel always gives the total resistance smaller than the resistance of any of the component resistors. Just play with it. 1 over R is equal 1 over R1 plus 1 over R2. Equivalent, let's say it's equal to R1 is equal R2 is equal to ohms. What we will get then? 1 over R equivalent is equal 1 over 2 plus 1 over 2, that is 1. So equivalent resistance is 1, definitely smaller than 2. A little bit more about batteries. A real battery is what we're actually using, but to solve equation it's a little bit more confusing, so we're using an ideal battery analysis. So ideal battery always maintains a constant voltage across the terminal, and the value of the voltage is EMF of the battery. Also, a real battery is equivalent to an ideal battery in series with resistor. That is a resistance of a battery. So this is internal resistance of the battery. It is easier to solve circuits if we split the real battery on two parts. EMF, ideal battery, and then tiny resistance next to it, right in series with the battery. So what's happening if we have a circuit with a battery, resistance, and here is a small internal resistor of a battery. How do we solve the circuit? Similar way, we have EMF, then we have Kirchhoff loop rule. Start at this point. So 0 is equal EMF negative I times R, negative I times RB. That's how we can simplify it. We can write it as EMF is equal I times R plus RB, or then I, current, is equal EMF divided by R plus RB. R is external resistance, and RB, our battery, is an internal resistance of a battery. Let's talk about what is potential difference across the real battery terminals. Ideal battery terminals are here, but for real battery terminals are here. We need to include its resistance. So we need to look at the voltage drop from this point to this point. We can simplify this idea as to look through the voltage drop, not this way, but this way. So it should be delta V, potential drop through real battery, is current multiplied by resistance, this resistance, external resistance. And current, we just find it out that it's equal EMF over R plus R battery multiplied by R. So if you're looking to find potential drop of a real battery, you have to multiply EMF, that is what's written on the battery, like 9 volts, and divide by sum of external resistance plus internal resistance of a battery, and multiply by external resistance. Obviously, if our battery is 0, that means we have ideal battery. Voltage drop through battery will be equal EMF divided by R times R, so it is EMF. So for ideal battery, when RB is 0, so there is nothing over here, just a wire, voltage drop is equal EMF.